Welcome guys, today I'm going to be showing you how to derive Brahmagupta's formula. It's a very famous formula discovered by Indian mathematician Brahmagupta in around the 7th century, and it describes the area of any quadrilateral inscribed in a circle, a cyclic quadrilateral. And the formula itself is very beautiful. It shows that the area will be the square root of the consecutive product of the semi-perimeter minus each of the quadrilateral sides. And remember, the semi-perimeter is just half of the perimeter. So let's get into deriving it. So to find an area of a quadrilateral, we're going to split it up first into two triangles. Like this, we're going to draw a diagonal, we're going to call it K, and we will have two triangles here on the top and the bottom. And so the area can just be expressed as the sum of the areas of these triangles. And remember that the area of a triangle with an angle included is the side times another side times the angle in between them over 2. So 1/2 times AB times the sign of, here we have alpha. And we're going to have the other one. It's going to be the same thing, C times D plus 1/2 CD. And remember again, property of a cyclic quadrilateral is that the opposite angles are supplementary. So this is going to be sine of 180 minus alpha, 180 degrees minus alpha. And if you look at the list of identities I included here on the right, the sign of the supplement, the sign of any angle is equal to the sign of its supplement. So here it's actually doesn't matter if we include 180, it's just going to be the same sign of alpha. So we can instantly factor this as well to be 1/2 sine of alpha times AB plus CD. This is actually what makes the whole formula very beautiful, the fact that it's a cyclic quadrilateral and we have these supplementary angles. Okay, so that's done. But we can also now relate these different sides in a triangle through this diagonal using the law of cosines. So look at this. We have the diagonal here, we call it K, and its square in relation to the other sides of both of the triangles is going to be as follows: a squared plus b squared minus 2ab times the cosine of the angle between them. This is the law of cosines. And here we have the same thing for the other triangle. And such, we are able to relate all four sides of this quadrilateral using the law of cosines. It's going to be c squared plus d squared. It's going to be plus 2cd cosine of alpha. This is also by another identity that the cosine of an angle is equal to the negative cosine of its supplement. And here we have this beautiful relation. We can then simplify it a bit more to get that a squared plus b squared minus c squared minus d squared. It's going to equal 2 cosine of alpha, instantly factoring ab plus cd. And I'm going to do something a bit strange right now, but later it will be useful in the derivation. We're going to divide both sides by 2, get rid of this 2 on the right side, and then take the square of everything. So then we get that it's going to be 1/4 of a squared plus b squared minus c squared minus d squared. All of that squared is equal to the cosine squared of alpha times ab plus cd squared. Why did I do this? You will see in a moment where this expression on the right side will appear again. So going back to our area as the sum of two triangles, we're going to factor it, we're going to use its factored form already, and we're going to square that as well. So from this expression right here, where the 1/2 sine alpha times ab plus cd, that's equal to its area. We're going to recall that and we're going to square it. So the area squared, the area, again, remember a is the area of the whole quadrilateral, what we're finding, is going to be the 1/4 sine squared of alpha times ab plus cd squared. I just squared this whole thing. So that makes 4a squared. To get rid of the 4, we're moving it out, equal to simply sine squared of alpha times this. But then remember the Pythagorean identity with sine squared plus cosine squared is equal to 1. So we can rewrite the sine squared as the 1 minus cosine squared of alpha. And again multiplied by ab plus cd squared. And if we factor it out, we get ab plus cd squared times 1, right? And also the same thing times the cosine. So yeah, plus the cosine squared of AB plus CD squared. And aha, look at this. Cosine squared times AB plus CD quantity squared. Isn't that what we have here from our law of cosines? That is equal to the very beautiful 1/4 times this whole expression of all three sides squared, all four sides, sorry. And so now we can keep writing this. We can substitute in our expression for the cosine squared of alpha times AB plus CD squared into a new one. And like that, we have completely gotten rid of the cosine. And from there, it's some beautiful algebra remaining to derive this expression for the root. So let's write it out. We get AB plus CD squared as usual, and it's going to be plus 1/4 times that. Squared plus B squared minus C squared minus D squared, all squared. Wait, how is it plus? Did I? Of course, sorry, this is not a plus, this is a minus. This is a minus, right? We multiply times negative cosine here. Sorry, how I didn't see that. Yes, it's going to be factored out this part. We get this squared minus the cosine squared. And so we get minus our expression of 1/4. There we go. There we go. From here, it will make a bit more sense. And so from here, we can once again get rid of this fraction of 1/4, which we don't want. We're going to multiply everything by 4. Remember, this is 4a squared. That becomes 16a squared now. If we multiply by 4, it is going to be 4 times ab plus cd squared minus the rest of this huge thing squared. And so we can continue even more now. Look at this. This is 4 times another perfect square. And look at our property right here. We have a squared times b squared is equal to a times b quantity squared. 4 is the perfect square of 2, so we can just basically root it and put the result inside. That's going to be 2 times ab plus 2 times cd squared. Right, we're just putting the 4 inside. This is already a perfect square. This result will be the same as this multiply. Makes sense. Minus the huge perfect square as well. B squared minus c squared minus d squared, all squared. Okay, so now we're done with the boring part. We can actually begin the fun part. Look at this. This is just a difference of squares. And as I have written right here as a reminder, difference of squares is as the following simple formula: a plus b times a minus b. So we can rewrite this difference of squares as a sum times a product. That is going to be, it's going to be 2ab plus 2cd minus first thing, 2cd. So yeah, let's do minus first. We're going to have minus a squared minus b squared. Remember, negative times negative, plus c squared plus d squared, all positive. Now it's going to be times basically the same thing, just with a positive. Plus 2cd plus a squared plus b squared, running out of space, minus c squared minus d squared. Oh, all multiplied together. And now we can notice something really cool. Look at this. Do you notice anything about perfect squares in here? Notice how c squared plus d squared plus 2cd. That is literally just c plus d quantity squared. So we can write that already. And the same exact follows for all of them. We get a squared minus b squared plus 2ab. That is not exactly a perfect square, but it is just the negative of a squared, a minus b squared, right? It's the negative of a minus b quantity squared, right? Because we multiply this, we get positive a, positive b, negative 2ab, but here it's the opposite, minus a, minus b, positive 2ab. And we can do the exact same move in the second bracket. We have a plus b squared, then minus, seems like, yeah, minus c plus c minus d squared. There we go. And that is all multiplied. And once again, we have a difference of squares. So we can simplify this even more as 4 brackets now. first we have c plus d, let's have minus a plus b, right? First we're subtracting from here. Then we are adding c plus d plus a minus b. Then we do the same thing here, difference of squares. We get a plus b first minus c plus d, and the same with minus d. A plus b plus c minus d. All right. And this is looking very, very beautiful. Notice how here we have A, B, C, and D all subtracted while the rest are summed. So if we just define a semi-perimeter now, this is where the semi-perimeter finally comes in play. If we define a semi-perimeter as following, A plus B plus C plus D over 2. Therefore, we get that the area we have 16A squared. Notice how this is just twice the semi-perimeter, right? There's no 2. And subtracting 2 of each of the sides. 2a, then we're going to have that 2b times 2c, right? Because this is twice the semi-perimeter. And we are first subtracting 1 to remove and then the other to remove. And so we get 2s minus 2b times minus 2c, and so on to minus 2d. All right. And now we are very close. Now what happens if we divide the whole thing by 16 again? We get something very cool. A squared is going to be, imagine dividing each of them by 2, 2s minus 2a over 2, and so on and so on. Because, right, 2 times 2 times 2 times 2 to the 4th power is 16. We have basically divided it by 16. So on, so on. And so we have finally discovered the formula. Dividing each of them by 2, we get s minus a times s minus b times s minus c and times s minus d. That is equal to a squared. And if we take the root of everything, we get the famous formula that area is the root of such semi-perimeters minus each of the sides. It's an absolutely beautiful proof of it, finding perfect squares using law of cosines, getting rid of the cosine. It is completely wonderful and shows the creative process which we can find the area of a quadrilateral. That is it for the video. Hope you enjoyed. Make sure to watch my video on deriving the formula for the sum of an arithmetic series. I will be very happy if you do that. And that's it. Thank you for watching.